Hello everyone, my name is Khushi from BSc Chemistry Honors 3rd year. Today we will discuss about metal ligand bonding in transition metal complexes. Transition metals have very good tendency to form coordination compounds or complexes, though many attempts were made by different workers to explain the bonding and structure of coordination compounds. The main credit goes to brilliant work of Werner in 1893. Werner proposed a theory which is commonly known as Werner's coordination theory. This was the first successful attempt to explain the bonding in coordination complexes. In recognition of his work in this field, Werner was awarded Nobel Prize in 1913. He explained the bonding in these complexes on the basis of two types of valencies of metal: the primary valency corresponding to oxidation state and secondary valency corresponding to coordination number. The secondary valency or coordination number determined the stereochemistry of complexes. However, the Werner's assumptions were not based on theoretical justification, and scientists started making attempts to find bases of bonding in these complexes. The first attempt in this regard was made by Sidgwick, who extended the Lewis theory of electron pair bond formation to explain the bonding in transition metal complexes. He suggested that metal ion atom accepts electron pair from ligands until it achieves the next noble gas configuration and gave a term effective atomic number. En is the total number of electrons possessed by central metal ion and the electrons gained by it from ligands. However, this theory lacked fundamental basis and simply gave emphasis on the stability of inert gas configuration in coordination compounds. With the advances in theories of chemical bonding, three modern theories of bonding in transition metal complexes have been developed. These are valence bond theory, crystal field theory, molecular orbital theory. In the present text, we shall discuss mainly crystal field theory of bonding. The valence bond theory has already been discussed in the previous classes. Valence bond theory. The valence bond theory was developed by Linus Pauling and assuming the bonding between the metal atom or ion and the ligands to be purely covalent. It presents a simple description of metal ligand bonding using hybrid orbitals of metal and the electron pair of the ligand. The basis of valence bond theory is that the appropriate vacant atomic orbitals s, p and d of the metal atom hybridize to give a set of hybrid orbitals which are directed towards the ligand according to definite geometry of the complex. The bonding in metal complexes arises when a filled orbital of the ligand containing a pair of electrons overlaps with a vacant hybrid orbital on the metal atom or ion, forming a covalent sigma bond called coordinate bond. In addition to a sigma bond, there is also a possibility of pi bond provided suitable orbitals are available on the metal atom and the ligands. The total number of metal atomic orbitals which undergo hybridization is equal to the coordination number of central metal atom or ion. For example, for coordination number 6 complexes, 2d 1s and 3p orbitals, that is a total of 6 orbitals of the metal atom, are involved in hybridization. The d orbital involved in the hybridization may be either inner n minus 1d orbitals or outer nd orbitals, giving inner orbitals or outer orbital complexes. For example, in case of octahedral hybridization, the orbitals may be 1 ns, 3 np and 2 nd, that is sp3d2 hybridization, or 1 ns, 3 np and 2 n minus 1d, that is d2sp3 hybridization. Similarly, for coordination number 4 complexes, tetrahedral structure can be considered to arise from bonding with 4 sp3 hybrid orbitals formed by the combination of 1 ns and 3 np atomic orbitals, or square planar structure arising from bonding with 4 dsp2 hybrid orbitals using n minus 1d ns and 2 np atomic orbitals. Some common type of hybridization of orbitals and their geometries are given in table. sp हाइब्रिडाइजेशन है और उसकी शेप क्या होगी, लीनियर होगी. sp2 में शेप क्या होगी, ट्रायगोनल प्लेनर होगी. sp3 हाइब्रिडाइजेशन है जिसकी उसमें टेट्राहेड्रल ज्योमेट्री होगी. DsP2 होगी स्क्वायर प्लेनर, DsP3 होगी ट्रायंगल बाइपिरामिडल, sp3d होगी स्क्वायर पिरामिडल, d2sp3 और sp3d2 होगी octahedral. Now we will discuss about limitations of valence bond theory. Valence bond theory successfully explains many stereochemical and magnetic properties of coordination compounds. However, it has many limitations. The main limitations of valence bond theory are it provides only qualitative explanations for complexes. It does not explain the color and electronic spectra of complexes. The theory fails to explain why some metal complexes in a particular oxidation state are low spin, that is inner orbital complexes, while some other complexes of same metal ion in the same oxidation state are high spin complexes. For example, in the complexes CONH3 6 3 positive and COF6 3 negative, the oxidation state of cobalt is +3, but the former is low spin complex and the later is high spin complex. It does not predict the relative stabilities of different complexes. We know that certain complexes are labile, in which the displacement of ligands take place rapidly, while some are inert, in which ligand displaced by another ligand is very slow. Valence bond theory does not explain the kinetic inertness of complexes such as chromium third and low spin cobalt 3 octahedral complex. It does not explain the variation of magnetic moment values with temperature. It does not take into account the splitting of d energy levels. It does not predict the relative stabilities of different structure. The valence bond theory does not predict whether the four coordinate complex will be square planar or tetrahedral. This can be explained only on the basis of magnetic moment values of complex. For example, the decision about the geometry of nickel second complexes depend upon the magnetic moment values. For example, nickel second ion has the electronic configuration 3d8. If the complex involves sp3 hybridization, it would have tetrahedral structure. For the formation of tetrahedral structure, the 3d orbitals remain unaffected and the complex is paramagnetic. On the other hand, if the complex involves dsp2 hybridization, it would have square planar structure. This is possible if two unpaired d electrons are paired up, thereby making one of the 3d orbital empty. There is thus no unpaired electron and the complex would be diamagnetic. It also fails to give a satisfactory explanation for the formation of square planar tetraamine copper second ion. The valence bond theory does not tell us why water and halide ion commonly form high spin complexes while cyanide ions form low spin complexes. To answer some of the above problems, let us discuss other theories. We will discuss about crystal field theory, CFT. The crystal field theory was developed by H. Beth and V. Blake. This theory is based on entirely different assumptions than the valence bond theory. As we have already learned, the valence bond theory considered the bonding between the metal ion and the ligands as purely covalent. On the other hand, the crystal field theory considers the bond between the metal ion and ligand as purely electrostatic. This theory is based on the assumptions that the metal ion and the ligand act as point charges and interaction between them are purely electrostatic. In case of negative ligands, anions such as Cl negative, Br negative, Cn negative, the interactions with metal ion or ion-ion interaction. If the ligands are neutral molecules such as NH3H2O, CO, the interaction with the metal ion or ion dipole interaction. For example, in case of complex ion CO F6 3 negative, the interaction are between CO3 positive and F negative ions, where in CONH3 6 3 positive, the interaction are between negatively charged end of NH3 molecule and CO3 positive. And the central idea of this theory is that the electrons of the metal ion in the environment of other ions or molecules, as for example with the lattice of a crystal, are affected by non-spherical electric field established by the surrounding ions or molecules. The electric field was called the crystalline field, but now it is called as crystal field. This is responsible for the name crystal field theory. Basis of crystal field theory. The basic assumptions of crystal field theory are the transition metal ion is surrounded by ligands with lone pairs of electrons. All types of ligands are regarded as point charges. The ligands may be either ionic or molecules. If the ligand is a neutral molecule, then the negative end of dipole is oriented towards the metal ion. For example, ammonia is a polar molecule having negative charge on N and positive charges on H atom. Similarly, water is also polar with delta charge negative on O and delta positive charge on H atoms. This interaction between the metal ion and negative ends of an ions is purely electrostatic. The bond between the metal and ligand is considered 100% ionic. The ligands surrounding the metal ion produce electrical field, and this electrical field influences the energy of orbitals of central metal ion, particularly d orbitals. In the case of free metal ion, all the 5 d orbitals have the same energy. These orbitals having the same energy are called degenerate orbitals. This means that an electron can occupy any one of these 5d orbitals with equal cases. However, on approach of ligands, the orbital electrons will be repelled by lone pairs of the ligands. The repulsion will raise the energy of d orbitals. If all the ligands approaching the central metal ion are at equal distance from each of the d orbitals, the energy of each orbital will increase by same amount. Therefore, these orbitals will still remain degenerate, but they will have higher energy than before. But we know that the d orbitals have different orientation, and therefore these orbitals will experience different interaction from the ligands. The orbital lying in the direction of ligands will experience greater repulsion, and their energies will be raised to greater extent. On the other hand, the orbital lying away from the approach of the ligand will have lesser interaction, and therefore their energies will be raised to lesser extent. Therefore, due to electrical field of ligands, the energies of 5d orbitals will split up. The conversion of 5 degenerate d orbitals of metal ion into different sets of orbitals having different energies in the presence of electrical field of ligands is called crystal field splitting. This concept forms the basis of crystal field theory. The number of ligands, coordination number, and their arrangement geometry around the central metal ion will have different effect on relative energies of 5d orbitals. In other words, the crystal field splitting will be different in different structures with different coordination number. The magnetic property, spectra, and preference for particular geometry can be explained in terms of splitting of d orbitals in different crystal fields. Thus, to understand the crystal field theory, it is essential to have a clear picture of the disposition of the 5d orbital in space and the geometrical arrangement of ligands around the central metal ion. We may illustrate this concept by considering the complexes with coordination number 6 and 4, which are very common. Shapes of d orbital. There are 5 d orbitals. These are designated at dx, y, dy, z, dzx, dx square minus y square, and dz square. The shapes of these orbitals are described below. The three orbitals dx, y, dy, z, and dzx are similar, and each consists of four lobes of high electron density lying in x, y, z, and zx planes respectively. These lobes lie in between the principal axis. For example, in case of dxy orbital, the four lobes lie in xy plane in between x and pi axis. The dx square and y square orbitals have also four lobes of high electron density along the principal axis x and y. It may be noted that orbital is exactly like dxy orbital, except that it is rotated through 45 degree around the z-axis. The dz square orbital consists of two lobes along the z-axis with a ring of high electron density in the xy plane. It may be noted that although dz square and dx square minus y square orbitals do not look to be similar, yet they are equivalent so far as interaction with the metal ions are concerned. The dz square orbital can be regarded as a linear combination of two orbitals, dz square minus x square and dz square minus y square, each of which is equivalent to the dx square minus y square orbitals. Crystal field splitting in octahedral complexes. In an octahedral complexes, coordination number 6, the metal ion is at center of octahedron and the ligands are at 6 corners. The three axes x, y, z point along the corners of the octahedron and are also shown. Let us suppose that the metal ion Mn positive has a single d electron in the free ion. When there are no ligands, the electron can occupy any one of the 5d orbitals because all are of same energy and are called eccentric orbitals. However, in the orbit octahedral complex mx6, all the 5d orbitals will not remain of equal energy. This can be easily understood by considering the shapes of these orbitals in the octahedral field of ligand. The comparison of arrangement of d orbitals that the two lobes of dz square orbitals and four lobes of dx square minus y square orbital point directly towards the corner of octahedron where the negative charges of the ligands are concentrated. The remaining three orbitals are oriented in between the axes. In the case of octahedral complexes, the former two orbitals are designated as EG orbitals, while the later three orbitals are designated as T2Z orbitals. T2Z orbitals. As the two ligands approach the central ion along the axis, the EG orbitals are repelled more than the T2Z orbitals. In other words, the energy of dz square and dx square minus y square orbitals increases much more than the energy of dxy, dyz, and dzx orbitals. It should be remembered that when the charge is repelled by similar charge, its potential increases. The greater the repulsion, the greater is the increase in energy. Thus, in octahedral complexes, the 5d orbitals split up into two sets, one set consisting of two orbitals of higher energy EG orbitals and the other set consisting of three orbitals of lower energy T2Z orbitals. The phenomenon of crystal field splitting in an octahedral complex is illustrated in the figure, as you can see. The energy difference between two sets of d orbitals T2Z and EG is called crystal field splitting energy and is symbolically represented as delta naught. Stands for octahedral knot. The magnitude of delta knot varies for different complexes. The crystal field splitting is also measured in terms of another parameter called dq. The two are related as delta knot is equal to 10 dq. These two parameters are very commonly used. It may be noted that the crystal field splitting occur in such a way that the average energy of the d orbitals does not change. This is known as barycenter rule, which is similar to center of gravity type rule. This means that the decrease in energy of set of orbitals that lie at the lower energy level must be balanced by corresponding increase in another set. Therefore, in terms of total energy 10 dq, the energy of each of two EG orbital is raised by 6 dq, and the energy of each of 3 T2Z orbital is lowered by 4 dq. In terms of delta naught, the energy of each of two EG orbital is raised by 3 by 5 delta naught, and the energy of each of 3 T2Z orbital is lowered by 0. 0.4 delta naught. The value of 10 dq or delta naught is measured spectroscopically. We observe that initially the energies of all the 5d orbitals are raised equally as shown in state second. This would be observed if the field created by the ligands were spherically symmetrical. However, the energies of d orbitals split into two sets because of different orientation of orbitals towards the ligands, as shown in state third. Crystal field stabilization, CFSE. We have learned that in octahedral field the energies of 5d orbitals split up. Three orbitals are lowered in energy and two orbitals are raised in energy. We know that the electrons always prefer to occupy an orbital of lower energy. For example, in case of d1 system, the d electron will prefer to occupy a T2G orbital and is therefore stabilized by an amount equal to 0.4 delta naught or 4 dq. The amount of stabilization provided by splitting of the d orbitals into two levels is called crystal field stabilization energy. Thus, in octahedral field, for each electron entering into the T2Z orbital, the crystal field stabilization is minus 4 dq, and for -4 dq, and for each electron entering into easy orbital, and the crystal field destabilization energy is +6 dq. Thus the CFSE is calculated as the algebraic sum of -4 dq per electron in T2G level and +6 dq for each electron in easy orbital. CFSE for various octahedral complexes. For D1 system, electron will be present in any one of three T2Z orbital. The electronic configuration may be written as T2Z1. The crystal field stabilization energy is -4 dq. For D2 system, the electrons will occupy T2Z orbital with their spins parallel in accordance with Hund's rule. The electronic configuration is T2Z2, and crystal field stabilization energy is for -8 dq. Similarly, for D3 system, the electronic configuration is T2Z3. Crystal field stabilization is -12 dq. For D4 system, there are two possibilities. All of four electrons may occupy T2Z orbital with one electron get paired. The electronic configuration may be written as T2Z4. Three electrons occupy T2Z orbital and a fourth electron goes to one of the easy orbitals. The configuration may be written as T2Z3 EZ1. The actual configuration may be decided on the basis of delta naught and the pairing energy, that is the energy required to pair the electron with one another. The configuration A is possible if delta naught is greater than P. These complexes are called strong field complexes because delta naught is larger. In this case, the complex has less number of unpaired electron and is called low spin complex. The configuration B is possible if delta naught is lesser than P. It is called weak field and the complex are called weak field complexes. In that case, maximum number of electrons remain unpaired and complex is called high spin complex. For a D5 system, there are two possibilities. All the five electrons may occupy T2Z orbital with two orbitals get paired. The electronic configuration may be written as T2Z5. This is possible if delta naught is greater than P, and the complex will be called strong field or low spin complex. The three electron occupy T2Z orbital and two electron occupy EZ orbital. The electronic configuration may be written as T2Z3 EZ2. This will be possible if delta naught is less than P and the complex is called weak field or high spin complex. The CFs in two types of complexes will be strong field delta naught Similarly, D6 and D7 system have two possibilities depending upon the relative magnitudes of crystal field splitting energy and the pairing energy of electrons. The D8, D9, D10 system have only one possible configuration. This is because if we assume the complex to be high spin, the first 5 electron would go to 1 each into 5d orbital and remaining 3, 4, 5 electron would fill the T2z and EZ orbital. But if we assume the complex to be low spin, the first 6 electron would fill the T2z orbital and the remaining 2, 3, 4 electrons would go into T2z orbital. In both cases, the configuration will be same. Therefore, there is only one possible electronic configuration for D8, D9 and D10 systems. The d electron configuration for weak field and strong field of octahedral symmetry are given in figure 6. The crystal field stabilization energy for metal ions having different configuration are summed up. It may be noted that for strong fields, the electron always pair up in lower level first, filling it before entering the higher level. For weak fields, each orbital, whether of high or low energy, receive one electron each before any pairing starts. Therefore, weak field configuration always have same pairing scheme as the free ions. Crystal field splitting in tetrahedral complexes. The coordination number for tetrahedral complexes is 4. Tetrahedral arrangement of 4 ligands surrounding a metal ion may be visualized by placing ligands on 4 of 8 corners of cube. The direction x, y, z point to center of the faces of the cube. From the figure, it is clear that the orbital dx, y, dy, z and dzx point between x, y, z axis, that is towards the center of the edges of the cube, where the orbitals dx square minus y square and dz square point along xyz axis, that is to the centers of the faces. It is clear that in tetrahedral field none of the d orbital point exactly towards the ligands, and therefore the splitting of energy will be less than that in octahedral field. The 3d orbital dxy, dyz and dzx are pointing close to direction in which the ligands are approaching, while the two orbitals dx square minus y square and dz square are lying in between the ligands. Therefore the energies of the three orbital will be raised while the energies of two orbitals will be lowered. Thus in the presence of tetrahedral field, the degeneracy of 5d orbital splits up as the two orbitals dx square minus y square and dz square become stable and their energies are lowered. These are designated as e orbitals. The three orbital dx, y and dyz and dzx become unstable and their energies are raised. These are designated as t2 orbitals. The magnitude of crystal field splitting is the difference between E and T2 orbitals and is designated as delta T. Delta T indicating tetrahedral complexes. It is also measured in terms of dq, and delta T is 10 dq. If we compare the magnitude of crystal field splitting in octahedral and tetrahedral complexes having same metal ion ligands and metal ion ligand distances, it has been observed that the crystal field splitting in tetrahedral complexes is considerably less than in octahedral complexes. It has been found that delta T is equal to 4 by 9 delta Note: reason for some smaller value of crystal field splitting in tetrahedral than in octahedral complexes. There are two main reasons for this. In tetrahedral complexes, there are 4 ligands, while there are 6 ligands in octahedral complexes. Therefore, lesser ligands produce less crystal field splitting. The crystal field splitting in tetrahedral field is about 2/3 of octahedral field. In tetrahedral field, none of orbital is pointing directly towards the ligand and therefore splitting is less. Since the magnitude of crystal field splitting in tetrahedral field is quite small and is always less than the pairing energy, therefore the pairing of electron will never be energetically favorable. Thus all the tetrahedral complexes are high spin complexes. No tetrahedral complex will low spin has been found to exist. It is interestingly to note that splitting pattern is inverted when octahedral is replaced by tetrahedral symmetry. CFSC4 tetrahedral complex. As we know that an electron always prefer to occupy an orbital of lower energy, since average energy of the d orbital does not change barycenter rule. Therefore in terms of 10 dq, the energy of each of the e orbital is lowered by 6 dq and the energy of each of the t2 orbital is raised by 4 dq. CFS E is therefore calculated as algebraic sum of minus 6 dq per electron in E orbital and plus 4 dq for each electron in T2 orbital. In terms of delta T, the energy of each E orbital is lowered by 3 by 5 delta T or 0.6 delta T, while each of T2 orbital is raised by 2 by 5 delta T or 0.4 delta T. Crystal field splitting in tetragonal and square planar complexes. The splitting of d orbital in tetragonal and square planar complexes can be easily understood from the non-splitting of d orbitals in octahedral complexes. This is because tetragonal and square planar geometry can be understood by withdrawing two trans ligands from an octahedral complex. This process is called elongation. Generally, we consider the removal of trans ligand along the z-axis as the ligand lying on z-axis are moved away. The ligands in the xy plane tend to approach the central ion more closely as a result of increase in metal ligand bond along z-axis and the repulsion from the ligands to electron in dz square orbital decreases, and therefore the energy of dz square orbital is decreased relative to that in octahedral field. At the same time, the metal ligand along x and y are shortened so that the d orbital in xy plane dx square minus y square experiences greater repulsion from the ligands and therefore its energy is raised. Similarly, the dzx, the dxz and dyz orbitals are lowered in energy because of decrease in repulsion effects along the z axis, while the energy of dxy orbital is raised. The resulting splitting pattern is shown in figure 10. This state represents tetragonally distorted octahedral structure, as you can see that in the figure. As the trans ligands lying along z-axis are completely removed, a square planar complex is formed. In square planar complex, there is further rise in energies of dx square minus y square and is dxy orbitals, and a further fall in energies of dz square dxz and dyz orbitals are shown in figure 10. It has been observed that in square planar complex the energy of dz square orbital falls even below the dxy orbital. The change of an octahedral complex to tetragonally to distorted octahedron and finally to square planar arrangements. It may be remembered that tetragonally distorted structure can also be obtained when the two trans ligands are brought closer to the metal ion. This is called flattening of an octahedron. Factors determining the magnitude of crystal field splitting. The following factors influence the magnitude of crystal field splitting. Nature of ligand spectrochemical series. The crystal field theory depends upon the nature of the ligand. The greater the ease with which the ligand can approach the metal ion, the greater will be the crystal field splitting caused by it. The ligands which cause only a small degree of crystal field splitting are called weak field ligand, while those which can cause a large splitting are called strong field ligand. Spectrochemical series is an experimentally determined series. It is very difficult to explain the order because it is incorporates the effects of both sigma and pi bonding. In general, the variation in the splitting is caused by a number of factors, such as small ligand can cause greater crystal field splitting because they can approach the metal ion closely. The ligands containing easily polarizable electron pair will be drawn more closely to the metal ion. The ligands which have greater tendency to form multiple bonds, such as Cn negative and NO2 negative, causes greater crystal field splitting. The very high crystal field splitting produced by Cn negative ligand, about double that for weak field ligand like halide ions. This is attributed to the pi bonding in metal. The metal donates electron from a field T to Z orbital into the vacant orbital on the ligand. The following pattern for increasing sigma donation is observed: halide donors, then oxygen donors, nitrogen donors, carbon donors. The common ligands can be arranged in increasing order of crystal field splitting delta. The regular order is called spectrochemical series. The order remain almost same for different metal ions. The spectrochemical series in increasing order of crystal field splitting is given below. Weak field ligands: iodine, bromine, isocyanide, chlorine, nitrito, F negative, OH negative, oxalato, H2O, EDTA, PY, double bond NH3, EN, dpi, orthophenol, nitrocyanide, and cobalt. In general, the ligands up to NH3 are weak field ligands, while those on right of NH3 are called strong field ligand. The order of spectrochemical series remains practically same irrespective of transition metal ions. Oxidation state of metal ion. The magnitude of crystal field splitting depends upon the oxidation state of transition metal ion. The metal ion with higher oxidation state causes larger crystal field splitting. This is done then is done by the ion with lower oxidation state. For example, the crystal field splitting energy delta O for COH2O6 3 positive complex, in which oxidation state of cobalt is +3, is 18600 centimeter inverse, whereas for the complex COH2O6 2 positive, in which the oxidation state of cobalt is +2, that delta O is equal to 9300 centimeter inverse. Similarly, for the complexes FeS2O6 3 positive and FeS2O6 2 positive, in which iron has oxidation state +3 and +2 respectively, the values of delta O are 13700 centimeter inverse and 10400 centimeter inverse respectively. This is clear from the following data, in which crystal field splitting energy for hexaaqua complex of metal 2 positive and metal 3 positive ions of first transition series. Now we will discuss type of d orbital transition series. The extent of crystal field splitting for similar complexes of a metal in the same oxidation state increases by about 30 to 50% on going from 3D series to 4D series. This increase is almost of the same amount on going from 4D series to 5D series. This may be explained on the basis that 4D orbital in comparison to 3D orbitals are bigger in size and extend further into space. As a result, the 4D orbital can interact more strongly with the ligands and therefore the crystal field splitting is more. Similarly, 5D orbitals are bigger than 4D orbitals and delta O for third transition series is more than that of second transition series. Geometry of complex. As mentioned earlier, the crystal field splitting energy of tetrahedral complex is nearly half the value for octahedral complexes. In other words, the value of splitting energy for tetrahedral complex in general is small as compared to the pairing energy P. The tetrahedral complexes are therefore mostly high spin complexes. Thank you.